Alright, so here is a brief introduction on identifying redox reactions and um, finding out the oxidation numbers for various compounds. So starting off, the element that loses electrons is oxidized, so loses oxidation, and the element that gains electrons is reduced, so gaining is reduced. And so there's a very helpful acronym called oil rig. Oil rig says basically if you're going to be oxidized, it's going to be oxidation is losing electrons, and reduction is gaining electrons. So for oxidation, this is going to be if you're losing electrons, you're going to be more positive, and for reduction, since you're gaining electrons, you're going to be more negative. So yep, this oil rig right here. And a reaction is a redox reaction if one element is oxidized and one is reduced. So basically that means if you have both an oxidation occurring and a reduction occurring, then it is a redox. If there's only one, say there's only oxidation occurring, that is not a redox. Same for reduction. If there's only reduction occurring, that is not a redox reaction. And so in a redox reaction, you need to know it has everything to do with electrons. Electrons are transferred from one element to another. All right, so taking a look at this first reaction right here, we can go ahead and try it. So we have 2K, which is a solid, plus a chlorine, Cl2, which is a gas, and that is supposed to be, and then the 2KCl, which is a solid. So determining oxidation numbers for both the reactants and products, we know that when an element is a standalone element, meaning that it's just alone by itself, we know that oxidation number is 0. Same for this Cl2 right here. It is also going to be a 0 since there's nothing attached to it. And taking a look at KCl, we can determine this based on the fact that since this is an ionic compound, meaning there's a metal and a non-metal attached to each other, the first metal takes a charge of its actual charge on the periodic table of elements. So K, potassium, has a charge of 1 plus, so then we know that the K is going to be a 1 plus as well. And so for K, we know it's 1 plus. And then taking a look at Cl right here, we know that since there's no charge on this whole compound, there's this invisible 0. So the charge has to equal to 0. So we can do this algebraically or we can do this in our head. But if you want to consider the algebraic way, we know that there's a positive 1 plus charge plus something for Cl has to equal 0. So then we just minus 1 from both sides, and we know that Cl is going to equal to a 1 minus charge in order to be 0 at the end, since we have a plus 1 already. So we know Cl is 1 minus. All right. So was an element oxidized? We have to take a look at our oil rig here. So oxidation is the loss of an electron. So, do we lose an electron? Yes, because if you take a look at K, potassium, you're going to put a K down here. We have a 0. We're going from 0 oxidation number to 1 plus, 1 plus, meaning that this is going to be more positive, more positive. Just put plus there. So if you're being more positive, you're losing an electron. So losing electron. So that means that this is being oxidized. So we can just put here oxidized. Well, it says it right here. So we know that K is being oxidized. Next, for reduction, we do know it's being reduced because we see a change in oxidation numbers. So for reduction, we know it's a yes because the Cl is going from a 0 to a negative 1. 0 to a negative 1. So this is becoming more negative, which means that it is gaining electrons because electrons hold a negative charge. So gaining electrons. Electrons. All right. So now we know that there's oxidation for K and a reduction for Cl. And so, if we take a look at the next question, is reaction 1 a redox reaction? Yes, because both oxidation and reduction took place. Both oxidation and reduction takes place. All right. Taking a look at the second reaction, we have Fe2SO4 aqueous plus KOH aqueous, and then we have K2SO4 aqueous and FeOH3 solid. So this is a little more complicated because we have multiple compounds and we have more than one element, like unlike this. So for oxidation numbers, we have to take a look at each individual element. So FeSO, KOH, and all the other ones as well. So starting with the first set, FeSO. Um, SO4, we know that on the back of your common ions page, we know that SO4, the sulfate ion, has a 2 minus charge. So that is a 2 minus. And we know based on one of our rules that oxygen has a 2 minus charge. So 2, and there's 4 oxygens. So negative 2 times 4 is negative 8, but it has to equal negative 2. So negative 8 plus sulfur equals negative 2. And so we know that sulfur is going to be plus 6. So based on this information, we can determine that since oxygen is 2 minus, sulfur is going to be 6 plus. All right. So now we know this, we just got to write it down in our box. 6 plus, and we know that the oxygen is a 2 minus in the start because that is one of our rules for oxidation reductions. And then for Fe2, we have to figure out if this SO4 molecule, let me highlight it, this sulfate molecule is a 2 minus and there's 3 of it. 2 minus times 3 is negative 6. But this whole compound has a 0 charge. That means we have to do something to this to make it 0. So we have two iron molecules in front. So 2 times Fe has to equal 0. So 2Fe equals 6, and therefore 1Fe equals 3 plus. Since this is a 2 minus times 3, which is a 9 minus 6, and divided by 2, and we get a single Fe, which is a 3 plus. Let me just erase this real quick. All right, so we know that is a 3 plus, and we got to write it down here, 3 plus. All right, taking a look at our second one, KOH. We know both O and H because H has a plus 1 charge based on one of our rules, and O has a 2 minus charge based on the rules. The whole thing's charge, 0. So we have to do K plus 2 minus plus 1 plus, so we're just going to exclude that plus, has to equal 0. So 2 minus and a positive 1 makes it K minus 1 equals 0. So therefore, we know then K equals 1 plus as our oxidation number. So just delete that. So then we know K is 1 plus. We know oxygen is 2 minus based on our rule. And let me just erase that. And H is 1 plus. So K is 1 plus, oxygen is 2 minus, and H is 1 plus. All right. Take a look at the product side now, this whole side. We know SO4 has a 2 minus charge. Okay, and this whole thing has a charge of 0. So we have to do, and we have 2K molecules. So 2K plus 2 minus equals 0. So we get 2K equals 2 divided on 2 both sides, and K equals 1. That's 1 plus. All right, so we determined our K. Just delete that real quick. So we know K is 1 plus. We know this is 2 minus. And so we know here on top, the oxygen, this is 2 minus. So if we have 2 times 4, since we have 4 molecules, that's 8 minus, plus S equals 2 minus. What do we have to do? We have to add 6 on the S, then 8 minus 6 is negative, or sorry, we have 8 minuses, and 8 minus, and then we have plus 6, then we get 2 minus on each side. So negative, so that's the oxidation for the whole sulfate ion, plus something for S equals negative 2. So then S has to be 6 plus. So we've determined S as well as 6 plus. So we can write it here, 1 plus, 6 plus, and 2 minus. All right, and our last one, we have FeOH3. We know O is 2 minus, and H is 1 plus. And we have 3 of those hydroxide molecules. So if we take into account the fact that we have 3 OHs and 3 Hs, we do a simple calculation. 3 times 2 is negative 6. 3 times 1 is 3. So negative 6 plus 3 equals negative 3 for the whole hydroxide. But this whole element, or a compound, has a charge of 0. So in order to neutralize this, negative 3 plus Fe has to be 0. Therefore, Fe has an oxidation number of 3 plus, making it all 0. So deleting this, we know Fe has a 3 plus charge. And so we can just write it here on the bottom box. 3 plus, 2 minus, and 1 plus. All right. So if we take a look at our oxidation numbers, we see from Fe to Fe there's no change. S to S there's no change. O to O there's no change. K to K no change. O to O no change. And H to H no change. Therefore, no electrons were moved. So, is there an element that is oxidized? No. So we can just put a not available here. Was an element reduced? No, not available. And therefore, is this a redox reaction? No. Explain how you know. Because there were no oxidations or reductions or reductions. And putting it to more scientific definition, there were no electrons that were exchanged or electrons that were transferred, making this whole thing not oxidized, or no element in this whole thing oxidized or reduced. All right, let's take a look at reaction number 3. Reaction number 3, we have CuS on the left reactant side. We have 2AgNO3. We have CuNO3 on the product side, and 2Ag on the product side as well. So our rules for redox reactions say that if a standalone element is present, their oxidation number is automatically 0. So we also know there's a standalone element right there, so we know that is also 0. Taking a look at our Ag and N and O first, we know that O has an oxidation number 2 minus. That's one of our rules. And we know that the whole NO3 compound, the NO3 ion, is nitrate, which is 1 minus. 1 minus. And so we have 3 oxygens, meaning that we have to do a 3 times negative 2, which is the oxidation number that we know for oxygen, which gives us negative 6 plus N has to equal the charge of the ion, which is 1 minus. So it has to equal -1. So N, we know, is 5 plus 5. All right, so we know N is 5 plus. So taking a look at Ag, we know that this whole compound is -1, and we have one Ag up here. We can ignore this because we're only looking at one mole worth of compound for this, because um, it does not matter for oxidation numbers how many of there are. We are looking at just one basic part of it. So we can consider that an Ag has to equal, or Ag and NO3 have to both be some number that'll lead to the zero charge that this whole compound holds. So Ag plus the -1 from NO3, -1 equals 0. So then we add 1 to both sides, and now we know that Ag has to equal 1 plus. So with that information, we can go back and assign this oxidation number of 1 plus and fill our box in. Well, we have a 1 plus, 5 plus, and a 2 minus. And we can also check this. We have 1 plus here. We have a 5 plus here, which is 6 plus total. And then we have 2 negative times 3, which is -6. 6 plus minus 6 is basically 6 minus 6, which is a zero charge, which also corresponds with the zero charge on our whole compound. Therefore, we know that all of these are correct. Moving on to CuNO3 Same deal as before. We know NO3, the nitrate ion, has a 1 minus charge. So we know oxygen already has a 2 minus. So 2 minus times 3 has to equal -6. And if -6 has to equal 1, -1, you have to do plus n. So n equals 5 plus. Okay, so just maybe I should delete it that way. Okay, 5 plus on the n. And if this whole nitrate compound is -1, 1 minus, and we have two of them, that's a 2 minus has to equal 0, or 2 minus plus Cu, the copper in front, has to equal 0, which is the overall charge of the whole compound. We know Cu has to equal 2 plus. Delete all that. And now we know Cu has to be a 2 plus. To be, the whole thing has to equal a charge of 0, which is invisible. So Cu 2 plus, we have N 5 plus, and O 2 minus. So taking a look at this, from Cu 0 to 2 plus, we are going from a charge of 0, and we're becoming more positive from 0 to 2 plus. And based on our acronym, oil rig, we know that a loss of electrons will make our whole element more positive. So we know that something was oxidized, and that oxidized was copper, because you're going from a charge of 0, or oxidation number of 0, to a 2 plus. So in this process, we are giving up more electrons, which means that we're losing electrons, which makes it more positive. More positive. So we know that Cu is oxidized, copper. Was an element reduced? Well, we know that we already have Cu down. Let's take a look at Ag. Ag is going from 1 plus to a 0. And we know that if you're going from a 1 plus to a 0, you're going from something that's positive to 0, which means that you're losing an electron. And we know that if you're losing an electron, if you're gaining an electron, you're going from a 1 plus to a 0. So based on this fact, we know that something was reduced, and that is Ag, because 1 plus to a 0 means that you're are gaining an electron. So If you're at a 1 plus charge, you have 1 plus, and you're becoming a 0, we're removing that positive by adding an electron. So it's a little confusing, but if you practice a lot, you'll get the hang of it. 1 plus moving to a 0. If you add an electron to this, then you become a 0 because you lose that positive charge. That means that the element that was reduced is Ag. So we have both oxidation and reduction, so we can confirm that it is a redox reaction because both oxidation and reduction took place. Took place. All right, let's take a look at the fourth problem. That is rather simple. SeF6O2 and SeO2 and F2. So based on this, we can just quickly calculate the fact that we know F is one of our rules. That is a 1 minus. 1 minus times 6 becomes negative 6. And in order for this whole thing to become a charge of 0, our 1 minus on F6, and this Se molecule has to be a 6 plus. So since we know that F fluorine, we have 6 of them, and each fluorine has a 1 minus oxidation number, and this whole thing has to be a 0 charge, we know that the Se is a 6 plus. Standalone elements, regardless of being Brinkelhoff, the diatomic, we know that single molecules are always 0. Same for this F2 right here, we know it's a 0. And O2 is one of our specials, so we know oxygen has a 2 minus oxidation number. 2 minus times 2 is minus 4, so negative 4. And there's one Se molecule to cancel it out to make it a 0, making that a 4 plus. All right. So taking a look at our Se molecules, we're going from a 6 plus to a 4 plus, 6 plus to a 4 plus. So in order to go from 6 plus to a 4 plus, we're becoming um, we're becoming less positive. So we're gaining electrons in order to make the number less positive. So that's a gain electron, and based on our oil rig, gaining is a reduction. So therefore, we know that Se is going to be reduced. And making a mental note of that, we're going to just put it to the side. But we know that is being reduced. Let's do it in a different color. All right. So taking a look at our F, we know it's going from a 1 minus to a 0. So if you're going from a 1 minus to a 0, you are doing what? You are gaining an losing an electron to make it less negative. So we know that this is losing electron because you have a negative here and you're giving that electron away and you're becoming more positive by moving from a 1 minus to 0. So if our Se was gaining electrons and our F is losing electrons, we can fill out our little chart here because we have found both of our elements that are oxidized and reduced. So if both of that exists, we know this is a redox reaction because the Se, the oxidation number of Se, goes from 6 plus on the reactant side right here to 4 plus on the product side right here. So Se, if you're going from a 6 plus to a 4 plus, you're gaining electrons to make it more negative. So oil rig says gaining is reduction, so it is reduced, and the oxidation number of F2, or sorry, we can just put F. F goes from, we have a 1 minus here, and we have a 0 here. So if your F is going from 1 minus to 0, you are losing electrons to make it more positive from a 1 minus to a 0. So we know losing electrons is oxidation. So F is oxidized. Horrible F. F is oxidized. And so this shows that electrons are transferred. So electrons are transferred in the reaction. And so this is a redox reaction in the end. All right. So the fifth one, quite simple on this as well. We know that F holds a 1 minus charge. 1 minus times 4 is negative 4, and there's 1 Si, so that is going to be a 4 plus to make the whole thing compound neutral. H2O, we know both of these. O is 2 minus, and H is 1 plus, and we have 1 plus times 2, which is 2 plus, and then 2 minus, which makes it a neutral compound. Moving on to SiO2, we know O2 is always 2 minus, unless it's a H2O2. It's part of H2O2, which is 1 minus, but you don't have to know that. So we have O2, so negative 2 times 2 is 4, and we have 1 Si, so this also has to be a 4 plus. For H and F, we know both of these, 1 minus on F and 1 plus on H, and they all add up to a charge of 0 to make it all neutral. So taking a look at our elements, we have Si, we have F4, we have H and O. So we have Si, F, H, and O as our choices. So starting with Si, we can take a look. So Si has a 4 plus on the reactants. Si has a 4 plus on the products, so we can exclude Si from our oxidation or reduction element. Next up, we have F. F has a negative 1 on the reactants and a negative 1 on the products, so we can also exclude F. We have hydrogen here, 1 plus on the reactant, 1 plus on the product. We can also exclude that. And oxygen, we have 2 minus and 2 minus on both sides, so we can exclude all that. So based on this, we know that is this a redox reaction? No, because no element is oxidized or reduced. And remember that for a redox, both oxidation and reduction must take place in order to be a redox reaction.